Well, hello everybody. Welcome to part 2 of our Electronics 101 and a half series. Now there's a couple things I want to preface before we start here, and that is that we are this, as I said in the first part, and I got a lot of comments on this, this is not about how to purchase and build this particular kit. Okay, this kit can be purchased from eBay. I think they have them on Amazon. I think you could get them on some of those other places. I don't really go to those other ones, but I heard like what is it, AliExpress and those places, they all sell them. If you want to order one, you can just search vacuum tube push-pull amplifier 6P14, I believe. And you should be able to come up with several different variants of this same amp. And again, they change. You know, it's not always the same amplifier. So that's why I'm a little bit ambiguous with how to download it. I can't just give you a link. It may not be there when you try to order it. So search it out. All of them are very similar, so you'll find out that they're all about the same. So the beginning of your amplifier is the mains power, right? Where the power goes in to the amplifier. Now, before we get into things like transformers and everything, I wanted to take a short time, and that's what this particular video is going to be about, to talk a little bit about the types of voltage. Particularly direct current versus alternating current. The first thing we want to establish is what is direct current and what is alternating current, and how do they act? What effects do they have on a circuit? Now, the first thing I'm going to do, I'm not going to get into what is a volt and what is an amp and what is an ohm and what is a watt and all that. Those are things that you can look up online. But what I am going to do is I'm just going to take a little clip off of Wikipedia and put it up on the screen with a brief description of what alternating current is and what direct current is. And I'll have you I'm just going to flash them up here for the second here. You can pause the video and you can read it over if you like. I'm sure that most of you that are watching this at least have a basic fundamental understanding of what volts and amps are. So with that in mind, what I want to do is I want to first of all show you a picture that represents volts. Okay, first we'll look at direct current or direct voltage, and then we'll look at alternating voltage and current. Now, why do we use current and voltage interchangeably in this terminology? Well, it's because you really cannot have one without the other. For instance, even your meter, when it is measuring, let's say, voltage, you have to have current flowing through your meter or through your test equipment to be able to see the voltage. And vice versa, there has to be a voltage potential present before any current can flow through anything, including your meter or any piece of test equipment. So when people say AC and DC, they're just meaning that the power, the energy that's there, is flowing in either one direction or it is flowing in alternating directions back and forth. And we'll see this here in just a minute. Now, the first thing we have to do is figure out, how can we look at volts? Okay, voltage is electrons, right? And how do we see an electron? It's a subatomic particle. It's so tiny, you know. So how do we see it? Well, what we do is we use test equipment. Now, many of you, or most of you who are interested in this channel, have seen something like this, which is a meter. And this meter is capable of reading both AC voltage and DC voltage, as well as current, both AC and DC. And all it will do is, when you place this across a voltage potential, like for instance your ubiquitous 9-volt battery, it will give you a number that represents how many volts or how much electromotive force there is of potential across that battery. Now, this battery is producing direct current. In other words, the current only flows in one direction all the time. It never changes. It's just constant. And as a matter of fact, if I try to measure AC voltage, it doesn't read anything. Okay, it'll pick up a little bit of noise from around here, but essentially there is nothing there because it's not alternating, it's direct. So you have to set your meter to DC to see it. Now, this is nice, it gives you a number, but it really doesn't show you what the voltage is doing, right? It just tells you how much quantity of it there is, but really doesn't tell you what it's doing. It doesn't give you a pictorial diagram of it. So what if I had something that could take a pen and it would just start moving across this piece of paper, and anytime I placed a voltage on this meter, the pen would go up. And the more volts I put on the probe, the more up it would go. The less volts, the less it would go. All right? So if I connect my battery, it would go up to 9 volts. If I disconnect my battery, it would go down to 0 volts. Okay? Well, that's exactly what an oscilloscope is. So let's take a quick look at it. Okay, we have our old analog oscilloscope connected up now. And what you see, this is called the trace. It's a little dot that's being projected onto the screen. All right? And it has a little amplifier connected in there. Right now it's sitting at 0 volts. This line across the middle represents 0 volts. So when there's no voltage in there, that little dot will just keep floating back and forth across here. But if I take my battery and I connect it to the probe, okay, let me pop the cover off the probe. See what happens? It goes up to about 9 volts. Now, how do I know that's 9 volts? Well, it has to do with how you set these knobs. You could set how many volts each little square represents. Go back and watch. I did a series on oscilloscopes. Go back and watch that, and it'll explain some of this to you. But this is just a quick review. So again, when the voltage is there, it goes up. When it goes away, it goes down. So see? And I can turn it on and off. And right now, I'm just turning this on and off. Now, this is not alternating because the voltage never goes less than 0 volts. It always goes 0 volts and positive volts. It never goes to a negative voltage. What is negative voltage? Well, what happens if I switch the leads around? So now I move it from the negative terminal of the battery to the positive. When I touch it, what happens? Now the trace goes down. See that? See that? Now, that was still direct current. It was just flowing in the opposite direction. Does that make sense? So it's just pulsing direct current. So as I turn this on and off, on and off, on and off, I'm trying to show you at the same time. See that? That's a pulsing direct current. That's not alternating. Now, if I was tricky enough and I could take this and I could go to positive, then negative, then positive, then negative, and keep switching it around back and forth, that is alternating current. And that's what we're talking about when we talk about the AC power that comes from your mains line out of your outlet when you plug it into the wall. Very important to understand that because as you saw, I had to rotate this battery and swap the leads around to change the polarity. All right? That's what that means. So that's AC voltage. And DC voltage is when the polarity never changes. The voltage can change, the voltage can go up or down, but it never changes polarity when it is direct current, or DC. And that's the difference between AC and DC. Now we'll talk about some things like offset and all that later on. But right now, that's the main thing I want to show you on this scope. Now let's go over to the digital scope where we can look at some other things. Now just like on the analog oscilloscope we were looking at, we have our trace. But on a digital scope, you don't see a little dot going across there, especially when it's going fast. It looks like this straight line. And it is sitting at 0 volts. 0 volts is the middle of the screen again, the middle graticule. We call each one of these little squares a graticule. And again, you can see that on my series on oscilloscopes. So if I turn on a signal, this is an alternating current signal. This is an AC signal. And right now, this little indicator here tells us that each graticule represents 1 volt. So you can see this goes from 0 to 1, 2 volts. So that goes up to 2 volts. Then it goes back down to ground, where it's 0 volts. Then it switches polarity and it goes down to negative 2 volts. Then it goes back up to ground. The process of doing that, where it goes from 0 to positive, to 0 to negative, and back to 0, we call that 1 cycle. Okay? And what's happening right now is that little dot that you were seeing on the analog scope, it's going past there very, very fast, and then it resets and sweeps back across. That's called the sweep. And as that voltage is alternating, that trace is going up and down, and it's drawing that picture. In this picture, this is a very special thing. You're going to see this a lot in electronics. This is called a sine wave. It's called a sine wave because the shape is sinusoidal, all right? And that's a trigonometric function, or trigonometric function. Excuse my terrible language. So that's what we're seeing right here. And if we count, just like we can count the graticules up and down to measure volts, we can count the graticules left to right to measure time. And right now we're set to 10 milliseconds per division. And if we move the beginning of this, just like so, we'll just put it right where it intersects right here, and we can count 1 cycle, right? 1 cycle would be from here to where it starts repeating again. So this would be 10 milliseconds, and this would be 20 milliseconds, and each little dot would be 2 milliseconds. So it would be 10, 12, 14, 16, just under 17 milliseconds. And what you'll find is that the frequency, which is how many times per second this thing goes through each cycle, is going to be 1 divided by the time. So if I take 1 and divide it by that 16 milliseconds, actually, if you measure it accurately, it's 16.7 milliseconds. And I take 1 divided by 16.7, you're going to come up with just about 60 hertz. And you can see the little frequency counter down here says 60 hertz. So this is your 60 cycle signal, or a representation of what it would look like coming out of your AC mains. Now, of course, your AC mains has a lot more voltage than this. It would go way, it's 110 volts they call it, but it really isn't exactly. We'll talk about that in a minute. All right, so we now know this is an AC sine wave, and it's 60 hertz, and that's what's in our mains. Now I'm going to show you a different signal. Now look at this. It's the same thing, right? It's a sine wave. It's exactly the same frequency. It's still 60 hertz. However, it never goes negative, does it? It only goes positive. So this is truly not alternating current, okay? Some people will still call it alternating current. They will say that it is an offset AC signal. So if you hear that term, that's what they're referring to. But it's equally an accurate statement to say that this is a pulsating or a sinusoidal DC signal, because it never changes polarity. All right? Now, there's a lot to that this affects, okay? So knowing where your reference point, where the ground, where the common point is when you're measuring something is extremely important, and we'll learn that in future installments of this series. But I want you to get your mind wrapped around that right now, okay? What we're seeing right here. Now there's a few different ways in which we can measure, or ways that we can look at this, okay? The first way is, how many volts does it go to in each direction? So we can count, it goes 1, 2 volts positive, and it also goes 1, 2 volts negative. So we could say that this is a 2 volt peak signal. That means it peaks out in either direction. It'll peak, there's the peak of the signal, at 2 volts. Whether it's positive or negative, it never goes more than 2 volts, absolute value, right? Now we can also say that the total change between this is going to be 4 volts, and that would be what we would call peak to peak. So when we measure from the negative peak to the positive peak, the peak to peak voltage of this is 4 volts. So if I connect my fluke meter, once again, my voltmeter, and I set it to AC volts, what do you think it's going to read? Is it going to read 2 volts, or is it going to read 4 volts? I'm going to leave this on here. I'm going to leave the scope connected. I'm going to turn the lights on. And I had the lights off so we didn't get glare on the screen. And you can see right here where I have this connected across this resistor. And it doesn't matter about this resistor right now, but you can see here's the AC signal coming in. This is our voltage. And here's our probe to our oscilloscope. And let's move our meter in here. And let's turn it on to AC volts. So we're set to AC volts right now. What do you think it's going to say? Is it going to say 2 volts? Or is it going to say 4 volts? Let's measure and see. What? It's not 2 volts and it's not 4 volts. What's it saying? That's kind of crazy, isn't it? It's saying it's 1.4 volts, isn't it? I wonder why. Why do you think that is? Let's think about that for a second. Okay, once again, we have our meter sitting next to our scope. So just so we can see we're not changing anything. And you can see right here where the scope is very clearly saying, and I'll zoom you in as much as I can. You can see where the scope is still saying, there we go, it's saying that we have 2 volts peak and 4 volts peak to peak. And you can see down here it says peak to peak is 4 volts, but it's saying this weird thing that its RMS is 1.4. And you notice up here, that matches right here, 1.4. Now we'll get into that here in a moment. That's our next thing, and then that'll be the end of this video. But I want to show you one more thing so you understand. If I take that signal away and now I go to my offset or my pulsating or my sinusoidal DC waveform, I'm still getting 4 volts peak to peak. Look, 1, 2, 3, 4, right? and it's still reading 1.4 volts RMS. However, if you look at the oscilloscope, it's saying 2.43 volts RMS. Now that's an anomaly of the scope in the way that it's sampling and measuring that voltage. Make sure you stay aware of that, because if you're looking at an offset AC signal and you have a scope that measures RMS voltage this way, know that this can be wrong. And that's right there's your living proof of it. So just something to know that can catch you. Again, this is Electronics 101 and a half. So that little bit of extra there, that's your half. For those of you just learning about AC and DC, don't worry about those things. We'll learn about those later on, right? So we've seen from our oscilloscope that this number represents the RMS. And what is RMS? I'll try to explain it to you here. All right, we have a little contraption here that's going to show us how DC and AC voltage relate to one another. This little gold-colored device is called a resistor. And what a resistor does is it converts electrical energy into heat energy. That's really what a resistor does. And depending on the value of the resistor, its resistance, it will have more or less capacity to do that. Now, what we're going to do is, you can see right now, this is sitting kind of at room temperature right now. And we have this meter on the left is connected to a temperature probe, and it's just showing us the temperature of this resistor right now. And because there's no current flowing through it, it's sitting about at its room temperature, or a little above probably, from me handling it and everything. Now what I'm going to do is I'm going to connect a direct current through it. I'm going to apply a voltage across it. And we're going to put 9 volts, just like that battery we were measuring with our scope early in the video, right? But instead of using a battery, which this doesn't have enough energy to drive this resistor, we're going to use a power supply, and you can see it's set at 9 volts. And you can see there's no current flowing right now because I don't have the power supply connected to anything. As soon as I connect that power supply across this resistor, current will begin to flow in one direction and one direction only. It'll never change polarity. Remember, we're putting direct current on here. So the current will continuously flow in one direction, uninterrupted, and there will be 9 volts across this. And we're not going to worry about how much current. But what's going to happen is it's going to take that 9 volts and that current, and it's going to convert that energy into heat. And the temperature that this thing stabilizes at is going to be a specific temperature based upon that amount of energy. Then we're going to connect up our 9 volts of AC and see how they compare. So let's do it. Let's connect this up. And you can see there's approximately 9 volts there, very close to it. 8.94. We can turn it up a wee little bit so we get exactly 9 volts. You can see it's very hard to adjust it perfectly. There we go, 9.01. And you can see the temperature of the resistor is beginning to rise. The reason the temperature is going up is because that energy is being converted into heat. Now what will happen is this will reach an ambient temperature with that amount of energy. And then once this thing is dissipating the heat at the same rate that the heat is being put in it, that'll be the temperature that this will stabilize at. And that's going to take us a few minutes for this to happen, because we got to wait for it to heat the whole body of this resistor up. So I'll come back in about 5 minutes or so when this thing stops climbing, and we'll see what temperature it stops at. We are now back, and to speed the process up, I lowered the voltage to 5 volts so it would stabilize more quickly and not get so smoking hot that you burn your finger. It's still pretty hot. It's 53 degrees Celsius, and you can see it's very stable at that now. And that's with 5 volts DC. So my apologies, we were going to originally do it at 9, but I decided to go with 5. So now let's put AC 5 volts on there. What we're going to do is we now have our AC sine wave on there, and we have I'm looking at 2 volts per graticule. So what we want is we want 5 volts once again, right? So 2, 4.5 of a graticule would be 5 volts. And if we go negative 5 volts, that's going to give us 10 volts peak to peak. But there's never more than 5 volts with respect to ground. And you can see right here, it says 10 volts peak to peak. I just want you to be clear on that. So we're putting 5 volts just like we were before. And we're going to see what happens to the temperature on this resistor. Now looking back down at this, I have the meter turned off. Let me turn it on. And remember, this meter is reading different. It's not reading 5 volts, it's reading 3.58 volts. And this is that RMS again. If you looked back up at that last clip that we did at the peak to peak when we were looking at the scope, if you notice, it was saying about 3.57 or 3.58 volts RMS. So I put the 5 volts on there, 5 volts peak. Let's see what happens to our temperature here. We're going to give it another 5 or 10 minutes to stabilize. And we're going to see if we get that same, what was it, 53 degrees or so Celsius. Let's let it stabilize and see. So as you can see, it's stabilized. And when we do 5 volts peak, it does not match the same temperature as when we put 5 volts DC. So now let's use this silly RMS thing and see what happens. Let's set it, the RMS, to 5 and see what happens to the temperature. There. That's pretty close. 4.98. That's good. And you can see this is already starting to climb. So let's see where it stops. All right, it's been about 5 or 10 minutes, and as you can see, we were what, at 53.2 or something like that? And now that we have 5 volts RMS, notice the resistor gets the same temperature, almost exactly, as the DC 5 volts. And that's really what RMS is all about. RMS is the average of that sine wave. And to get the average of the sine wave, you can go through all the math, but it turns out to be the square root of 2. So if you want to find the RMS of the peak of a sine wave, so what that turns out to be, 1 over the square root of 2 ends up being 0.707 roughly. So 0.707 times the peak will equal the voltage. And if we take that 0.707, all right, times that 5 volts peak that we were at originally, there's that 3.53 volts again that we were looking at. And conversely, if we take 5 volts and you times it by the square root of 2, and the square root of 2 is 1.414, times 1.414, you get about 7.07 volts RMS, or 7.07 volts peak. So in other words, we need about 7 volts peak to get 5 volts RMS. what I'm driving at is the RMS of an AC signal is equal to an equal amount of DC voltage. So 5 volts RMS will do the same amount of work or create the same amount of heat in this resistor as 5 volts DC. Pretty cool, huh? And that's why we do that. And that's all we're going to do with this lesson right now. It's very important that we understand the difference between the peak and the RMS of our incoming line, of our mains voltage. The next lesson, we're going to actually look at turning that AC signal into a DC signal again. And we're going to find out why that peak and RMS values are so important to know when we're building a power supply. I hope you like this first part of this series. And until next time, I wish you all peace, joy, happiness, and good health in your lives. And we'll be back real soon with another part. Take care, everybody. Bye-bye.